Welcome back to the MEP Academy. In today's video, we're going to break down one of the most important formulas in all of hydronic heating and cooling: how to convert GPM into BTU per hour, and how to reverse the formula to find GPM when you already know the heating or cooling load. This simple formula is used every day by HVAC designers, estimators, technicians, and project managers, and by the end of this video, you'll know exactly how to apply it in real-world situations. And here's something many people overlook. One piece of this formula doesn't just change your BTUs, it can also change your pipe size, pump horsepower, and even the cost of the entire system. I'll show you which part of the equation does that later in the video. Let's jump into the fundamentals. The core formula. Hydronic systems rely on one universal relationship: BTU per hour equals 500 times GPM times delta T, where BTU per hour is the heat transfer rate, GPM is the water flow, delta T is the temperature difference, and 500 is the water constant used throughout HVAC. This simple formula applies to hot water, chilled water, radiant loops, air handlers, fan coils, everything. Why the constant is 500? Let's quickly explain where the number 500 comes from. Water weighs 8.33 pounds per gallon. It takes 1 BTU to heat 1 pound of water by 1 degree Fahrenheit. There are 60 minutes in an hour. Multiply those together. 833 times 1 times 60 is equivalent to 500. That's why this constant works across all hydronic systems that use plain water. Converting GPM to BTU per hour. Now let's look at how to calculate how much heating or cooling a coil provides based on flow. Example 1. Heating coil output. A heating coil receives 4 GPM of hot water. The entering temperature is 180 degrees Fahrenheit. The leaving temperature is 160 degrees Fahrenheit. So delta T equals 20 degrees Fahrenheit. Plug it into our equation and we get BTU per hour equals 500, which is our constant multiplied by 4 GPM times 20 degrees delta T equals 40,000. This coil delivers 40,000 BTUs per hour of heating capacity. Example 2. Cooling coil load. A chilled water coil has a 10-degree water temperature drop and flows at 18 GPM. BTU per hour equals 500 times 18 times 10 equals 90,000. That's equivalent to 7.5 tons of cooling. Converting BTU per hour to GPM. Now let's reverse the equation. If you know the heating or cooling load, you can determine the flow rate required to serve that load. Just rearrange the formula. Required GPM for heating. A small office requires 32,000 BTUs per hour of heating at peak load. System delta T equals 20 degrees Fahrenheit. GPM equals 32,000 divided by 500 times 20 equals 3.2 GPM. That's the hot water flow required for that space. Required GPM for cooling. A conference room needs 75,000 BTUs per hour of cooling. Chilled water delta T equals 12 degrees Fahrenheit. GPM equals 75,000 divided by 500 times 12 equals 12.5 GPM. So you need 12.5 GPM of chilled water flow. Common mistakes to avoid. Here are a few common mistakes people make. Number 1. Using the air temperature difference instead of the water temperature difference. Number 2. Forgetting glycol corrections. A 30% glycol system reduces the multiplier from 500 down to about 450. Number 3. Mixing heating delta T with cooling delta T. Cooling coils often use 12-18 degrees Fahrenheit. Heating coils often use 20-30 degrees Fahrenheit. Many existing cooling coils were designed around about 10 degrees Fahrenheit delta T, but modern high-efficiency designs and ASHRAE 90.1 typically push toward 15 degrees Fahrenheit or higher chilled water delta T. How delta T affects pipe size. Quick example. Here's the quick example I mentioned in the beginning, and it's an important one. Say a space needs 100,000 BTUs per hour. With a 10 degrees Fahrenheit delta T, you need GPM equals 100,000 divided by 500 times 10. GPM equals 20 GPM. That typically requires around 1 1/4 inch or 1 1/2 inch pipe. But if you increase delta T to 20 degrees Fahrenheit, the required GPM is cut in half. GPM equals 100,000 divided by 500 times 20. GPM equals 10 GPM. Now the pipe size can drop to 1 inch, and the pump horsepower is lower too. Now, while increasing delta T can reduce your GPM, pipe size, pump horsepower, and installation cost, there is a trade-off. A higher delta T can sometimes increase the cost of source equipment, because boilers, chillers, and coils may need larger heat exchanger surfaces or higher supply temperatures to achieve those higher temperature drops. So delta T is always a design balance between piping cost and equipment cost. Final thoughts. With one simple formula, BTU per hour equals 500 times GPM times delta T. You can determine how much heat a coil delivers or how much flow a space requires based on its design load. This formula is one of the building blocks of hydronic HVAC. If you found this video helpful, be sure to check out our HVAC and plumbing estimating spreadsheets to streamline your construction bidding process. Check out our HVAC, electrical, and plumbing construction forms to help you run your business, and explore our online courses for in-depth training.